Okay. Yes.
Could you please unlock the pages?
Yes, I can. Yes.
Thank you.
I can for these ones. Of course, when we start, yes, I can. I should have done this. No. Ooh. Did I just manage to close down one there? That's annoying. So that's class notebook. Review student work. March assessments. Thank you to those, the majority of you who put it in the right place, did what I asked. There were very few problems with this. Next. Oh, so I've got to unlock both of them because, okay, so page locking, unlock all of those. Apply changes, come on. Should have thought of this before. Applying changes. Okay. All right, talk amongst yourselves. It's taking this time. Okay, and that was that one. I need to unlock that as well. Okay, I have now unlocked them. It might take a little while to come through, but I'm not. Okay, the very first question. Loads of you, Michael, are you there? You're another one. We did an Esther on this one. Quite a lot of you did. It doesn't say calculate the eigenvectors and eigenvalues of 11, 4, minus 24, minus 9. Okay? It doesn't just give you a matrix and say calculate the eigenvectors and eigenvalues. I'm pleased to say that a lot of you showed me you would have been able to do that very well, but it's more work than you needed because you have been given one of the eigenvalues, or rather you've been asked to show it. So if you're showing that something is an eigenvector, you don't actually need to derive it. All you need to do is show that you understand what an eigenvector is. So if you take the vector 1 minus 2 and pre-multiply by that matrix, you get 11 minus 8, you get 3 on the top, you get minus 24 plus 8, you get minus 6. Now, you know, hopefully, and I think this is true, you all know what an eigenvector is. You know that it's the vector that means when you apply the matrix to it, you get a multiple of the original vector. So 1 minus 2 is an eigenvector. With eigenvalue 3. Now, sure, for B, shortcuts aside, you are after solving the equation, the characteristic equation. And you'll get something that factorizes. Hopefully, you're looking to see one of the answers is 3. The other one is, I think, minus 1. But you don't need, Esther and others, you don't need to find the other eigenvector. So once you've found the other eigenvalue, you don't need to spend time finding the other eigenvector. Are there any? So I'm not screen sharing with you. Maybe you can see it, but I bet some of you can't. Yeah.
Because the question is saying is I show that. So how can we just use it as given?
I haven't used it as given. I haven't used it as given. I have multiplied the vector 1 minus 2 by the matrix 11, 4 minus 24 minus 9 and got 3 minus 6. Okay? I didn't know. Whatever vector you give me, I could have done that first step. I can multiply any vector I like by a matrix. If the resultant vector is a multiple of the first vector, then it is by definition an eigenvector. So I haven't used anything in there. I haven't used the fact that it is an eigenvector. I didn't know it was an eigenvector until I saw, oh look, it's 3 minus 6. That is 3 times 1 minus 2. Therefore, it is an eigenvector because this is a multiple of this, which means therefore it's an eigenvector. Does that answer your question? Was that Robert?
Yeah.
Does that make sense, Robert?
Yeah, thanks.
Okay, then you do need to solve the characteristic equation, and those of you who tried it, you all showed me you know what you're doing. Does that make sense to everyone? I don't want to leave, because I think some of you kind of, a few of these places, you'd have done so much better in this test, and that's fine. I think matrices is particularly susceptible to taking the wrong approach, getting the right answer, but spending a long, long time on it. Rich, I wouldn't be mentioning Esther over and over again if I wasn't confident she was doing absolutely brilliantly, because I was very impressed with what I saw. But she has at every stage, I think, tried to find the hardest way of doing it. Okay, and Cindy, you did it here. Is Cindy with us now?
Yeah.
Okay, so what Cindy did is basically set up the matrix, and what others did is set up the matrix M, A, B, C, D, E, F, G, H, and observed and multiplied each of those eigenvectors to see, knowing what you'd get, and did a whole load of algebra to get to the answer. But it's missing, and it's fine. So basically you showed from first principles you could get the answer. Those of you who did it that way, by the way, with lots of algebra, I'm impressed that you managed to pull it off. It would have scared the hell out of me for 3 marks, but you persevered. This is actually testing and understanding, and I was really delighted the number of you who got this. If I think of this as being my matrix of eigenvectors, I know that M, which we'll call U, so M, 1, 1, 1. Equals. Now, if I multiply that matrix of eigenvectors by the matrix, then it must be, if these are all eigenvectors, if the eigenvalue is 1, minus 2, and 3, I must get 1, 1, 0. I'm already doing more than I need to, by the way, for those who didn't quite spot this. So I've got that. Okay, what you've got to remember is that's U, and that's U minus what? No, that's U, that's not U minus 1, ignore that. So we've got MU equals, now this is the bit you've got to remember, it's that where this diagonal, it's that diagonalisation. Let me write it out. I suppose I'm reteaching diagonalisation. Now the eigenvector, the values are 1, minus 2, 3. So if you've done it this way already, then fine, that's great. If you didn't get this, can you just take a little bit of time just to check that if I do the matrix times U, convince yourself with one entry, if I do the matrix times U, I must get U times D, this diagonal matrix. U times D, remember this diagonal matrix has the property that if you post multiply by D, it will multiply each column by that number. So 1, 2, 0, 1, 1, 0, 0, 2, 1 times this diagonal matrix will give you 1 minus 4, 0, 1 minus 2, 0, 0, minus 4, 3. So if we do, I keep forgetting you're not actually watching me, you're only watching the board. If you multiply those two matrices together, you should see that you get a matrix that I've drawn with the big green arrow. So I didn't explain that very clearly. Does anyone need me to explain that more clearly? It's really down to whether you've understood diagonalisation. Okay, no one said anything. I can't always see your hands. So, okay. Well, then that means that M equals U, D, U minus 1. So this question was a disguised way, and it's basically telling you, if you know the eigenvectors and eigenvalues of a matrix, you can work out the matrix by using this theory of diagonalisation. So I think this is a really important question. It's why I put it in there. I hadn't done one like this before with you, but now I have, and I'd say that's really important. You know the eigenvectors, you know the eigenvalues, you can find the matrix. So well done to those of you who went straight to the answer. Well done to those of you who did a little bit of work to get there. Now, if you had loads of time, what you would now do is work out the inverse of u. Is Belva with us yet? No? Okay.
Yes, sir.
Yes. If you had loads of time, you'd work out the inverse of u by hand, but what should you do?
Wait, what?
So if you had loads of time to work out the matrix M, you would have to work out the inverse of matrix U by hand, but what should you do?
Should you find the determinant of the matrix?
If you were doing it by hand, that's what you would do. But if you're in an exam and you're in a hurry, what should you do at this stage here? I've just put an asterisk. What should you do to calculate M?
So you could use the calculator.
You use the calculator. And I did my best, guys, to help you with that by sending an email beforehand warning you to use a calculator where you could. It's only 3 marks. You can tell you've done quite a lot of work to get to this n equals u du minus 1. If you've written down what d is, and you've written down what u is, and you know n equals u du minus 1, surely that's got to be worth at least 2 marks. It's worth precisely 2 marks. Getting the inverse is worth a mark. Finding the inverse by hand is a fiddly thing. This is one of the reasons you are required by the regulations to have a calculator that does the inverse of matrices. It's so they can ask you questions like this that don't take you hours to get the inverse. So you just have to know how to use your calculator. So I've said it a few times. If you still don't know how to use your calculator fluently, make sure you do, because you've got 1 mark to multiply 3 matrices together, including finding the inverse of one. Okay? Any questions on that? Well done to those of you who knew all that, and well done to those who got it right, doing it by hand. It's just it slowed you down. Any questions? Okay. Now here's the thing that I think almost no one spotted, though they still got the answer right. For B, some of you misread the question. Read it again. The image is 14. We're trying to find the volume of the original. We know the image, the volume of the image. We don't know the volume of the original. We know the volume of the image is equal to the determinant of the matrix times the volume of the original. Is there anyone who's unsure of what I've just written on the board? That's what I take to be crystal clear. Okay. So what you've got to do is calculate the determinant of M. Now, granted, you have your calculators, so you're allowed to do this. You found M, you plug it into your calculator, you find the determinant of M. How can I look at what is on the board in front of you? I can look at what is on the board in front of you without calculating, without even knowing what M is. I can tell you that the determinant of M is minus 6. How did I know?
That's the determinant of D.
Good. And how can I show that the determinant of the determinant of the diagonal matrix is the same as the determinant of the matrix? Now you may just have remembered that as a fact. Did you remember that as a fact, Michael?
No, I understand it because U has the determinant of 1. So yeah, that's
But, okay, so it's not absolutely. I mean, I am supposed to have learned it as a fact, but I've forgotten it. U doesn't necessarily have a determinant of 1. It might do in this case, but what I do know is the determinant of M equals the determinant of U times the determinant of D times the determinant of U minus 1, right? Because I do know the determinant of M equals the determinant of U. So I know the determinant of N is the same as the determinant of M of U, D, the inverse of U. I know that the determinant of AB is the same as the determinant of A times the determinant of B, and I know that the determinant of U minus 1 is 1 over the determinant of U. So actually, the determinant of a matrix is just equal to the determinant of its diagonal matrix, which is a cool result. Any questions on that? Okay, Piers, how do you find the determinant of a diagonal matrix?
It's just equal to the product of the leading diagonals.
That's right, you just find the product of the leading diagonals. Okay, and that's something that I told you, so it's something you should learn. So you can make it a bit quicker. Don't grant it, you've got it on your calculator, that's okay. So the volume of S is actually 14 over 6. Okay, I promise I'm not going to go through all these questions in huge detail. Right, this one, for some of you, this was a bit of a car crash because you didn't quite fully interpret the question. So, most of you didn't get at least that it was the simultaneous equations like that. Minus 1, 3, minus 1, yeah. Most of you weren't there. That's how to do it. Okay. Does not have a unique solution. And you must show your reasoning. So what does not have a unique solution imply?
Sir,
Yeah.
I didn't quite understand this question, but after I gave it some thought, isn't that means that the determinant of a matrix is 0?
That's right. Because to solve this, and this was another one where we had a few people taking a really long route, and it's really important to stop and think about this. To solve the equation, you would multiply by the inverse of the matrix. You know that, right? In general, if I put a number, if I put k as 5 in there, and you wanted to solve that equation, you could do it on your calculator by multiplying the vector, the solution vector, the solution vector by the inverse of the matrix, and that would give you x, y, and z. Does that make sense? Michael?
Yeah.
Yeah. Now, because it does not have a unique solution, now if we multiply it by a matrix, if we multiply the right-hand side by a matrix, we'll get an answer. So it does not have a unique solution, must mean we can't multiply it by a matrix. And the matrix we were trying to multiply by was the inverse matrix. Well, if we can't multiply by the inverse matrix, it means the inverse matrix does not exist. Under what conditions does a matrix not have an inverse? It's the determinant is 0. If it had an inverse, it would have a unique solution. If it does not have an inverse, so we've got to find the determinant equals 0, and that gives us k equals 3. So now we know the determinant equals, the k equals 3. Any questions so far? Lucy, are you following this?
Yes, I'm just taking notes.
No, that's fine. I can't say that wasn't pointed out. Just remember you struggled with this one. So, okay. So we know that k is 3. Now, some of you then did the following, which does the go, so it's a sheaf. Unfortunately, it does say determine the complete solution to this system of equations. That does help to think geometrically here. It's not required to do the first part. Determine the complete solution. If you have realised that there's no unique solution, but there is 2 possibilities. What are the 2 basic possibilities? Or you could say 3. What are the possibilities for there being no unique solution? What does that mean? Geometrically, what would that look like?
They could all be parallel, they could be in a prism, or they could be in a sheaf.
Fantastic. So you could have, if there was a pair of 2 or 3 of them, they don't all have to be parallel. If there was a pair of them that was parallel, or all 3 was parallel, then there would be no place where they all intersected. So they would be inconsistent. If the three of them were not parallel, you could have a triangular prism and they would not all intersect at the same place, and they would be inconsistent and they would have no unique solution. Or they could all intersect at a straight line, and that gives you a sheaf of planes. So we can't go it's singular, therefore it's a sheaf. You need to show it, and determine the complete solution means find the equation of the line in this case. So we know that k equals 3, so we can rewrite, and I am going to do this because some of you I think were trying it but sort of just forgot how to do it. I am going to rewrite, and I know what's always confused me when I'm trying to solve these problems or when I'm trying to teach them, and I don't know if this is the same for you. But the thing is, your teacher has sort of introduced you a method to solve simultaneous equations using matrices. We've started off using matrices, and suddenly we're back to writing it in terms of x's and y's and normal simultaneous equations. Well, that is because we know we are now considering the case where there is no inverse. And therefore, our matrix method breaks down a bit. So we just go back to good old-fashioned algebra, with an eye to the fact that either they're consistent or they're inconsistent. Okay, now what we're going to do is we're going to eliminate equations 1 and 2. We're going to eliminate the same variable from any two pairs. It doesn't matter what you choose. I'm going to do equation 1 doubled plus equation 2, and that gives me, shout if you see me make a mistake, please. But it's the strategy. Think about what I'm saying. I want to have two equations in two unknowns. That's what you do when you solve an equation, isn't it? A simultaneous equation. We're trying to solve it, even though we might think something dodgy is going to happen. So I've eliminated x from that. I'm now going to try and eliminate x from 1 and 3, for example. So 3 times 1 minus 2 times 2. I'm bound to make a mistake here. 3 times minus 3y minus, I'm getting minus 5y plus 3 minus 3z minus z. And I'm very much hoping that 3 times 1, 9 minus, yes, minus 1. Oh, what does that tell us? That result I've just written up, what does that tell us?
There are inverse solutions.
Yes, but well, okay, I suppose that's a way of saying it. Do you remember I said we should have this question as to whether they're consistent or inconsistent? We've got 3 solutions, 3 equations. You're right what you said. We've got 3 equations. They're consistent. But that is, of course, the same as saying they have infinite solutions in this case. So that implies consistent. Because it's possible at this stage that you would get 5y plus z equals 2 and 5y plus z equals 3, which would mean inconsistent. So consistent. So we have now proved that all 3 planes do intersect, but they don't have a unique solution. Therefore, it's intersects in a line. But we still haven't finished, and this is where some of you fell down, because we haven't determined the complete solution to this system of equations. Now, if we know it's a line, the complete solution is the equation of that line. So all you need to do now, let's take equation, let's call this equation 4. We've got, let's see, what am I going to do? I've got 5y plus z equals 1, so I've got Z equals, trying to remember what I did. I've got Z equals 1 minus 5y. Well, I'm now going to take, that's equation 4. I'm now going to take any of the other equations. I'm going to take, I think, equation 3, which gives me 3x plus y minus z, minus 1 minus 5y equals 5. And that gives me 3x. Shout if you see a mistake, you've really got to be on the ball. One of the 3x plus 6y. I mean, I'm more interested in getting the basic strategy here. Equals 6. So x equals, I think, 2 minus 2y. Okay. So I've now got, because remember, you now need to know what the equation of a line looks like. Now we could have, equation of a line could be something to do with x equals something to do with y equals something to do with z. That's the Cartesian equation of a line. I don't particularly like that. I prefer the vector equation. So all I'm going to do is say r equals, right, let's take a point. The easiest point is when y equals 0. So a point on the line is 0, and there's a 2, and there's a 1. And I'm going to say let y equal lambda. You'll probably want to come back and have a look at this. And I get minus 2, 1, minus 5. Though you could also arrange it in the form above. Okay. If the finer details aren't clear, is the strategy clear? Does anyone need me to go through the strategy? I'm going to leave you time to look through the details yourself. I've written all this up in neat for you, as well as giving you the mark scheme. Any questions on that? Okay. Right. I'm just going to do one thing for you here. This was a lovely question. 4 was lovely. I've not seen one like it before. Okay. So I found it interesting to see a question. I mean, I've seen the theory of this sort of stuff before. I've not seen one like it before. I believe A is easy, but rather like the first one, a lot of you spent a lot of time doing stuff you don't need to do. B, I think some of you did it by inspection, which I guess is allowed, maybe even advisable, if you can. But just be clear, you can solve that. That's 5 equals minus alpha plus 2 beta. So it's a pair of simultaneous equations. So you can solve alpha and beta. You can find alpha and beta. And then it's the third part, which is totally unfamiliar. It says without calculating m squared. Now, I know why you did it. Some of you decided to diagonalise m and write it as u du minus 1. And then you kind of square that because you remember about calculating the powers of matrices. So it's u d squared u minus 1. All that's great, but when you type that into your calculator, you have ended up calculating m squared, haven't you? Does that make sense? And you get no marks for it. Well, actually, I might have given you 1 mark if you got the answer. Does that make sense? Someone say I'm not making sense, or I am making sense? Yeah.
Can you show how you do this one?
Oh, I'm going to show you how to do it, yeah. But I want you to understand why saying m equals u d squared u minus 1 doesn't give you the credit, because you have basically calculated m squared, even if you haven't written it down. If you type it into the calculator, it will calculate u d squared u minus 1, which is m squared. Does that make sense? What I said?
Yeah.
Yeah, okay, thank you.
Yeah.
So what you should do here, and it was nice, okay, well, it's nice. We've got P equals, can someone shout out what alpha was? I'm only going to do the first step and you can do the rest. What's alpha?
Alpha is 3 and beta is 3.
Okay, so I genuinely didn't know how I was going to tackle this. So I thought, well, how about starting off with MP? You know, if I can't get MP, I'm not going to get M squared. So I wrote MP. New factors. Okay, so that's 3mv1 plus 4mv2. Now, what's special about m of v1? Maybe going right back up to the start of the question. Come on, what's special about matrix M times the vector V1?
You get the vector that is also in line with V1.
Yeah, because V1, the point is V1 is an eigenvector. So V1 is an eigenvector, which means this is actually, and I'm aware, and I've got good reasons, but I'm aware I never came good on my promises to show you exactly what diagonalizing was all about. And this is one of the useful things that eigenvectors. Come on, M times V1, because V1 is an eigenvector, M times V1 is a multiple of that. Can you remember what lambda 1 was? Lambda 1 equals 2, was it?
Yeah, 2 and 5.
And lambda 2 equals 5. So MV1 is 2 times V1. And MV2 is 5 times V2. So if you write a vector as the as a linear combination, it's called, of two eigenvectors, it makes it really easy to work with that vector. And so this is sometimes what's used. If you know you're going to be using matrix M, if you can write a vector as the linear combination of its eigenvectors, you've got some n. And so you see, you can just repeat that. You can, so m squared p equals. So it's using the fact that they are eigenvectors. And the clue was that you started the question with eigenvectors, so it's a good bet that eigenvectors come into it. Okay, let's see. Okay, row operations. All right, this is interesting. If you did it the clumsy, crap, rubbish way, which most of you did, and got the answers right, I have to give you full marks. Even though I don't want to. This was not an exam question, it was an AQA topic test question. In an exam question, it could have said, you must not expand the determinant and put some restrictions on it. So if you did it the clumsy, rubbish way but got it right, you get all the marks. If you did it the clumsy, rubbish way and made even a single slip, you don't get any marks at all. Because what you're supposed to do is use factorising determinants, which we spent, I gave you a nasty exercise on it. I'm going to do this here. I'm going to take a factor of x out of the first. And I suspect most of you knew it, and you thought, you know, well, this is going to be easy enough to multiply by hand. And you're right, a lot of you did it and got it right. And I've taken the factor of x out. And take a factor of x out. Now, you might argue that this is no quicker and no better, and I don't mind you saying that, but there are questions where it's the only way to do it. So you do need to understand it. I'm now going to subtract, there's a million ways of doing it, I'm going to subtract the second column from the first, and you should remember that that leaves the determinant unchanged. Is there anyone who wants to ask anything about what I've got on the board so far? So it's a lot of me talking on this, I know. Okay. Well, if you're sure about that, well, look, we can take another factor out, x minus 1.
So can you explain it again, please?
Can you tell me where you want me to start my explanation? Right at the start? Or
no, the second step.
This step here? Yeah. Okay. So one of the row operations is you can add or subtract two columns from each other. I have subtracted column 2 from column 1. And I'll explain how I noticed. That took me a little while to work it out. I did work through this paper. You've got to learn that if you add or subtract two columns or two rows together, it doesn't change the determinant.
Yeah.
You're going to learn if you add a multiple of one row to a multiple of another one. It doesn't change the determinant. So I haven't changed the determinant by doing that. Is that okay? Does that answer your question?
Yeah, thanks.
Okay, and that gives me. Now that would be enough to get me full marks, but I suppose I've started, so I'll finish. I'm on a roll. I'm going to do the same thing again. And I can take another factor of x minus 1 out, because of a difference of 2 squares.
So can you change the color, please? Because
Sorry, yes, I can see that. It's just I don't know what happened there. Sorry, I can see that's gone on. Okay. And then you can finally, I mean, you can still simplify it a bit better. You could add the second row to the top row, or add the top row to the second row to get some more zeros to make it even easier. But I think for the sake of moving on, that'll do. And then you expand that determinant. You know, you've shown that you can do what you're supposed to do. Now, I get that in many ways that's certainly conceptually harder than just multiplying the damn thing out. But there are times when multiplying the whole thing out could really be too difficult. That I'm not sure that testing this is ever going to work, because it's almost always going to be easy enough to multiply it out for a 3 by 3 matrix. Okay. Okay, 6 I'm not going to go through. 7 I'm not going to go through. 9 I'm not going to go through except for one little bit. 8 I will go through. This was the hardest question for me. When I looked at it, I thought it didn't look that hard. And then when I tried it, I realised it did require a bit of thought. Well done to those who got it. So the obvious first thing is to work out, is to use the e to the x equals 1 plus x squared over 2 factorial plus x cubed over 4. That's the obvious first step. And then the obvious next is to go e to the minus x equals 1 minus x plus x squared over 2 factorial. It's the obvious next step. It turns out not to be the right next step. It is the obvious one. Any questions on that so far? And so x e to the minus x equals x minus x squared plus x cubed over 3 factorial minus x to the 4 over, sorry, that's 2 factorial. And then you can hope that the person who's marking it is a complete idiot and write that the limit of x e to the minus x, x tends to infinity equals naught. You could try that. You could hope the person who's marking it was daft as a brush. Can you all see why that's a big, that's not going to get you any marks for that part. Everybody see that?
Justified.
Sorry, Piers?
You haven't justified it.
Yeah, I mean, I haven't. I mean, you know, I can actually see by look, as I'm sure lots of you can, I can visualise the kind of graph of x e to the minus x. I can do it in words, as I think Lucy tried, which I get, you know, e to the, and it's the sort of language I have used up to the point where we got to the rigorous definition. You can sort of say e to the minus x decreases quicker than x does, and that's a nice intuitive way of seeing why the limit must be 0. So I'm very happy if you can look at that and say, x e to the minus x, the limit must be 0 as x tends to infinity. But you've got to justify it using the sort of methods I've shown you. And this thing here, x minus x squared plus x cubed over 2 factorial minus x to the 4 over 3 factorial. I can't tell by looking at that tends to 0. I have no idea what it tends to. That's the whole point of this question. Okay? It could tend to infinity, it might tend to 0. Sadly, Ethan, you're not here yet, are you, Ethan? Good, we can have some fun at Ethan's expense because you are going to be watching this video. Ethan did this. He wrote, well, as x tends to infinity, x is infinity. And then as x tends to infinity, x squared tends to infinity. So you've got infinity minus infinity. Well, what does x cubed over 2 factorial tend to as x tends to infinity? Oh, it's infinity. And what does x to the 4 over 3 factorial tend to? It's infinity to the 4, that's infinity. And then I'm hoping that you are all in your rooms laughing. Though to be fair, this is the sort of thing that physicists and engineers do all the time. That is also completely unacceptable. It was a nice try. Maybe he was hoping I was really tired while I was marking it. He can tell me after he's watched this video, because I haven't recorded this, I should have told you. 10. Now, this question did come from a different exam board. There is one thing I'm not sure about. I don't know if Kelvin's still here listening. I certainly wouldn't mind if he wasn't. He might be able to help me here, because it's something I'm not sure about. So what actually you have to do is do it as x over e to the x, which is equal to x over 1 plus x squared over 2 factorial. Now, we have done things a bit like this before. When we're doing something a bit more rigorously, we can't leave ourselves saying, well, it's infinity over infinity, it's 1. We have to know exactly how the top and the bottom behave. So this is what I said, which according to the OCR1 scheme wouldn't have been valid. I'm sure it's okay for us, but maybe Kelvin can identify there's something wrong. I said this. Okay, at the moment I've got infinity over infinity. I'm not going to call that 1, I'm not going to call that 0. I am going to divide the top by x. And I get 1. And I'm going to divide the bottom by x. Okay. Well, the numerator is 1, so it tends to 1, so the top tends to 1. And the denominator tends to infinity. Because they're all positive. When they're alternating sign, I've no idea when it comes to the bottom, they're all positive. As x gets larger, the bottom gets larger. So we've got the limit of x tends to infinity is 0.
So,
Okay, now does that make
0?
Sorry?
I don't see why it is 0.
So we've got something. We've got the limit. Well, okay. Tell me this. What's the limit of as x tends to infinity of 1 over x?
0.
That's 0. So we have got something that is tending. We've got something of that form. We've got 1 over something tending to infinity.
Oh, okay. I see.
Yeah. The 1 over x tends to 0. Fine. 1 over x tends to 0. We don't worry about that. The rest will tend to infinity. Here we can't quite do that because we've got infinity over infinity. Now, the mark scheme I've got it from says you can't divide by x, you've got to divide by x squared. So what they have done is like that, which leads us to the same thing. It's just the top would then tend to 0 and the bottom would tend to infinity, which I can't see why it matters. If anyone can see why it matters, please do tell me. Okay. So I think that was the hardest one. Yes?
So can we use L'Hopital's rules to differentiate both sides?
You can't, not because you're not allowed to use L'Hopital's rule in general, but because it tells you to use the series expansion.
Well, yeah, expand it first and then use the L'Hopital's rule.
No, I mean, you're using the series expansion for this. If you were allowed to use L'Hopital's rule, then using the series expansion has just made things harder rather than easier. So it's got to be done pretty much like this. Certainly for the sake of this question, yeah.
Yeah, because I expand each of x as you did, and I got x over 1 plus x, x squared over 2 factorial, and then I use L'Hopital's rule. So
yeah, okay, I can see what you're doing, but in which case, did you actually need to use the series expansion? No, you didn't. You could have just used L'Hopital's rule. So you haven't really used the series expansion. You put the series expansion in there in order to have a series expansion there because the question says, but you haven't used it. It hasn't helped you. Okay, you could have just done it with L'Hopital's rule. So no, you have to do it sort of pretty much like this.
okay, thanks.
Okay. But I will say it came from another exam board that has a different balance of the amount of suspends and limits. So, you know, it was unfamiliar to me as well. I thought it was a nice question. Now, B was the one I was particularly keen on. I'm going to finish now. B, you forget about the limits first and integrate it by parts first. So if you, well, let's I said I'd leave it. But let's do it really quickly. The integral of, because it was in, I suppose I do need to explain the limiting process part. Because some of you got really muddled, and it can be really muddling with your working. Let's find the integral of x minus 3 e to the minus x. Get the limits first. Let me just get my solutions. Gone on longer than I wanted to. Longer than you wanted me to, not sure that's true. Teacher. Okay, so I'm just going to show you. So what I have done in my solutions, which are up there, just as a strategy, and then we'll talk the limiting process, I have first of all used integration by parts to integrate the thing without the limits. It's just too fiddly to get the notation right for most of us. And I've ended up with this expression. And you certainly can't get credit for this answer unless you've done the integration by parts correctly. Even if you end up with the right answer, it's a show that. So you kind of need to get to that stage. And then you say, therefore, the integral between 3 and infinity is the limit as a tends to infinity of that. I'll just leave that on the board for you to think about. See what I've done. Some of you got the right answer, but your reasoning was invalid. You got the integration by parts a little bit wrong, or you hadn't shown the limiting process in detail, which is what this question is about. The lims bits aren't just fancy extras, they're absolutely critical to it. Okay, I'm going to stay here. So I just very, very quickly, I want to talk about 9b. Okay, 9b, it wasn't supposed to be a mean trick question. In fact, it ended up being rather easier for you than I'd intended. We haven't done the inverse trigonometric substitutions for integration. It is something we will do. So therefore, I looked at that and go, I know there's a way of doing that using inverse shine. They won't be able to do it using inverse shine because we haven't done that method. I have put on the board the method I was hoping that you were going to try, and I knew it would be quite difficult for some of you. I'd like you to look at it when you're reviewing this and make sure you understand it. Very well done to anyone who did that. Of course, stupid me, I've forgotten, of course they've got it in the formula book, and not only do they have the inverse shine, they've also got it as in terms of logs. So you can actually not do most of this work and you can come straight to the answer using a formula in the formula book. And that is certainly allowed. It's one of the acceptable, in fact, it's the easiest, it's the best answer. So those of you who I've never seen anything like this, Dr. Langdon's forgotten a piece of the course, but look, it's in the formula book, I can use this. You are absolutely right. It's just I haven't forgotten a bit of the course. I was hoping you were going to do it this way. I'd forgotten it was in the formula book, that's all. Okay, so have a look at that. Right, sorry to go on for so long. What I'm going to do now is I'm going to throw the solutions and the mark scheme into the content library. I'm going to stay on the call. You only need to stay on the call if you've got questions for me. Okay.